Why? Because one of the bounds is infinity. Okay, so let's take a look at this here. So one way to show something converges is to actually find the limit, right? So if you could integrate this and find the answer is 7, therefore it converges. Like if the answer is 7, then it converges, right? Let's just look at this though. Sine of theta as 4 goes to infinity. What is that between? Sine. Why is it doing this? Don't do the thing now. Oh, come on. Okay, so sine of this has to be less than or equal to 1, has to be like this, right? So what's the biggest it could be? Let's just right? It's biggest. So you know that this has to be less than or equal to 4 to infinity, not alpha, 4 to, come on, pen, you are just killing me today, Smalls, you're killing me today. To infinity of 3 plus 1 over alpha d alpha, right? Like that? So that's the same thing as what? Integral of 4 to infinity of what? Dx, right? Hold on, so you know it's alpha like this. Hold on, so that's the thing, that's a ceiling, right? So this is correct so far. It might not help us, but does this 4 have any influence on convergence or divergence? No. So you know that's the same thing as 4. You could take it out like this, right? Yeah. 1 over alpha d alpha, right? Like that. What can you tell me about that? That diverges? Does it diverge? Does it diverge? I'm just asking. It does diverge, but here's the thing. So we just showed that something greater than it diverges. Does that help us? No. But still, that was a great idea. That there's one other thing we can do. So we just showed something that's greater than it diverges. That doesn't help us, right? The ceiling blows up. That doesn't help us. So instead of going to the ceiling, what could we go to instead? Hold on. Yeah, I'm telling the story. Answer the pieces as we go so everybody can follow along, right? We just proved it's smaller than something that diverges. Doesn't help us. Let's go to the other extreme. What's the smallest sign could be? 2. I hope not sign could be 2. I hope. So you know that this thing right here is greater than what? 4 to alpha over what? 2 over alpha d alpha, right? Correct? But what do you know about this? Does that change anything? What does this do? It diverges, right? Well, now the key thing though is what? We're now greater than diverges. So therefore, what does it do? It diverges. You just showed it's greater than something that diverges, so it diverges. Before, it was smaller than something that diverges, which doesn't help us. You need it to be greater than diverges or smaller than what? Converges. Exactly. Very good. Okay, and then you want to see is that number 9, you said? Number 9, this one right here? Is this it? The slope field one? Yes? Who asked about number 9? I'm not going to do it if someone didn't ask about it. Who asked about 9? You did? Good. Okay. So it says slope field is shown in figure 1110. Sketch the solutions.
Really see that.
Okay, so you're okay with this one? You go to this point and then you just follow the path?
Yeah.
Okay. From your sketch, write the equation of the solution path. What was this one? When you did 1, 0? What happened when you went to 1, 0? It's like a what? Over, what is it, 1, 0 or 0, 1? Negative 1, 0. Sorry, negative 1, 0. So that looks like it's right about here, right? Mm-hmm. So what does it look like that solution is? The solution is the equation y equals minus 1, it looks like. I'm sorry, the pen is dragging a little bit, so it's going to be a little messy. That's what we guess it is. That's the guess. But then for C, what does it say to do? Check your solution by substituting into the differential equation. Okay, so what is the differential equation right here? We know that dy dx is what? Equals x plus y. Yeah. Again, this is going to be messy, I apologize. But so what can you do now? Well, checking a solution is going back to the equation, right? You need to integrate. You can't integrate this nicely yet because it's not in the right pieces yet. dy should be attached to y, and dx's should be attached to what? X's. So what can we do here? Do you remember what this is called? There's there are separable differential equations, and is this a separable differential equation? So differential equations you have to be really careful with. Be really, really careful with, because if they're not separable, it's really hard to actually find the integral. Generally speaking, you're going to have to deal with separable differentials. So the way you can do this, you'll notice if you looked at did you look at the answer key? Yeah. I gave you the answer here. It says, if y equals negative x1, then y prime is negative 1 and x plus y. What do? They just check that specific solution. They don't actually try to integrate this. There should be a note here because what? It's not separable. What?
That one solution.
Yeah, I know. It's not very specific. Now, separable is pretty nice. We're going to practice that today. You basically want to get something dx with all the x's in here, right? You want it to equal something dy with all the y's in there, and then what do you do to both sides? You integrate both sides, but you have to separate variables first. You're going to do that. Almost guaranteed you'll have to do that on the BC exam. I don't write it, so I can't guarantee it, but you will separate variables. Absolutely. This is non-separable. It's a pain. So how would you do it by hand? I don't remember off the top of my head. I can't remember what you do with this type of non-separable. Go ahead.
How do you do that?
Again, you want to separate it. You're like, okay, dy is equal to x plus y dx, right? Yeah. No, we can try it. So dy is equal to x dx plus what? Y dx? Okay. So now what? Now you're like, okay, dy minus y dx is equal to x dx. Now what? Nothing. You're like, great, thanks, thanks. So that's the point. I don't remember. You could look it up. I'm sure there's some nice how-to. Why is this part of our section?
Because
4 is not in the domain of the function. It's not in the domain. So if you're trying to integrate to 4, you need to take it as a limit. And then why is this one right here? Well, it's pretty straightforward because what's in both the top and the bottom? Negative, yeah. The hardest part about this one is treating everything that's a constant actually as a constant. Your brain tries to try to turn everything into a variable. A is not a variable, A is a constant. B is not a variable, B is a constant. This is still single variable calculus. What's the only variable up there? X, exactly. So we won't do that, but I want to get into the new stuff today because it's real fun. I think it's real fun. So first of all, let's talk about this. So this is something you're going to have to be able to do. So it says show that y equals a plus c e to the kt is a solution to that equation. What type of equation is that? This is a differential equation. Why is it a differential equation? What's the simple definition of differential? It has talks about a rate of change. That's it. Lots of things are differential equations. The first thing you need to do if you're going to find a solution is think to yourself, solution means integrate and separate. You have to separate, you have to separate, you have to separate. So when you do this one, can you actually separate it kind of nicely? Yeah, you do the division, and then, oh look, what's going on both sides here? So that was just division from there to there. What did I do to get from here to here? What did I do? I integrated. Now, what was the constant that I added in there? I added a c. Theoretically, could I put like c1 on the left and c2 on the right? Sure. I integrated on the left so I could add a constant. So what does c represent? C represents just the collection of all the constants that accrue, right? Okay, what do you do now if we need to isolate y? That's the whole point, right? What do I need to do now? Put it into what form? What form does it need to go into now? We're trying to isolate y. What's that called? What form is that? Exponential form. So it's going to be e to what power? Kt plus c is equal to what? Y minus a. So you end up with y is equal to a plus e to the kt plus c, like this. So what they do now is since those exponents are being added, what's the trick? Not the trick, but it's just a plus e to the c, e to the kt, like this. And what do they turn e to the c into? That's just, it's redundant, not redundant, but they just turned it into a constant c. Theoretically, we could have chosen a better letter, like, let's call it d, right? Let's call it d, and then turn it into c. You know what I mean? The other way you can index is just by literally indexing it c1, and then if you need a new constant, call it c2. If you need a new constant, call it c3. So have we proven that this is a solution? Yes, this is just another way of writing that. This and what's below it are the same thing. They're just different forms. They describe the same relationship. It's a really common differential. What does it mean to sketch solution curves? Just to make sure everybody's 100%. Yeah, you follow the marks. So if I picked a point, let's say right, I don't know, like right here, what's that going to look like? It kind of looks like this, right? What happens if I picked this one right here? It's going to go like maybe like this, something like that. You follow the current. This just means follow the current.
When you were drawing that one out, couldn't you have gone just in the other direction? Whatever, like.
Oh, it's really hard. It depends on which points I pick. So yeah, depending on your visualization, you might think it actually does something like this, depending on how close you are, right? It's hard to see sometimes. So it's sometimes, but like here, it really looks like it's going to go like something like this, right? It kind of looks like there's an asymptote right there, right? So it has to behave like there's an asymptote on those like oblique asymptotes. But plotting is just following the current. That's it. Now, this was something that Tomas referenced, and it's something you need to be able to do. It's really, really good practice. It says one of the slope fields in figure 11.2 is the slope field for y prime is x plus y divided by x minus y. Which one? How do you go about identifying the slope field? One way is you could try to solve that differential and see if that helps you. Solving the differential is rarely helpful when matching to a slope field for two reasons. One, the integration could be really, really, really hard. And two, you might just be back doing the same type of analysis. What kinds of points should you look at if you are doing this one? Like what types of points? Like when you see this differential and you want to eliminate graphs, one thing you could do first. What types of points could you look at?
C has like horizontal.
Oh, look at that. Like C has a horizontal something, right? Has a horizontal something like that. So that's y equals a constant, right? And that's something. Well, let's look at the differential. Is there anything about the differential we should maybe notice? What?
So only look at that because this x plus y on the top. So when x equals negative y,
The slope is what?
0.
So you looked at the top. I like this. And this is still not behaving. Great. It won't change.
You look at the line.
So when y is equal to negative x,
Yeah.
y prime is equal to 0, right? So y equals negative x. Could you graph that on all of these? Yeah, y equals negative x is that, and y equals negative x is that, and y equals negative x is that. What's the only one where that it seems to match? Which one is the only one where, what does a slope of 0 mean? What type of line is that? Horizontal, right? Look at all these. Are these all horizontal right here?
Yeah.
So which one does it look like it is? It looks like it's B just sheerly by process of elimination on this one, because look at all the other ones. What's going on at all the other ones on the diagonal? Are they all 0? No, they're not. So the really big thing with matching a differential to a graph, find certain characteristics that can automatically eliminate many of them. Another thing I would look at, what about the denominator? Look at the denominator, x minus y. What happens if x equals y? What's the derivative? Undefined, right? So when y equals x, it's undefined. Well, look at this one. What is undefined slope going to look like? Straight up and down. Is that what's happening?
Yeah.
Yep. You see that? Look at all the other ones. Well, kind of looks like it, but look in the middle here. Are those straight up and down on the diagonal? Nope. So it wouldn't be that one. So it really looks like it's B. So matching, don't just a curve right there. When you plot solutions, they're really useful. Now, there are some specific aspects of logistic curves that are really important. What's one specific characteristic in there? Well, we talked about one of them, which is this. That's generally the what? Carrying capacity. That's the carrying capacity. There's another interesting point that's fun to find. What's the other interesting point? The turning point. So like this right here, right there, that would be like the time at the what? What's going on there? The max what? It's the max rate of change, right? So that's like when the population is growing the fastest. Where do you think that occurs in relation to the carrying capacity? If this is a logistic curve, it actually happens where? It's halfway. It's halfway, exactly. And then what happens if the population is above the carrying capacity? It's going down, right? Now, when you graph real data, is it this smooth? No. Generally speaking, population is going to go up and it's going to go down. It might spike. There might be an introduction of something that blows up the population. There's a uber classic example of this. And it happened, I think it was with the Yellowstone. Do you ever hear about the wolves in Yellowstone? I'm pretty sure it's the wolves in Yellowstone. So the elk population was, I think the elk, I don't remember what started it originally, but it was decided that the wolves were a problem. So what do? They just like wiped them all out. What happened after they wiped out almost all the wolves? What happened to the elk deer and elk? What happened? They exploded, right? But then what happened after that?
They didn't have enough food, so they started dying?
The population crashed, right? There was like a mass crash, right?
Yeah, there were too many.
There were too many. There was no selection of the weak out from the herd. So then they reintroduced wolves. The wolf population got back up, and then you ended up with overall a stable, healthy elk population. It's fascinating. So there's all these different factors that go into play. So real life never looks this clean, but it models it. It models it. So plotting these solutions, you can just start at the point, and then what do? Go with the flow. That's literally what you do, both directions. You go with the flow. Okay, so let's go to notation land, everybody. Let's go to notation land. Let's go to notation land. Okay, everybody just internalize that for a second and get over the immediate, like, oh God, what's going on? So find me the next 4. Just do P3 all the way to P3. Stop there.
What's the equation again?
Negative x over y. Do it carefully, please. Carefully, please. There are Euler's formula equation, programs for your calculator. I'm 50-50 on whether or not they're actually useful, because if you rely too much on the formula, if you get asked like a detailed question about the process, you might not have studied it enough. But what's that last P3y value? 0.9698, something like that?
Yes.
Like that, 9698? Got to go to at least 3 or 97, depending on how you round. On the AP test, they actually accept both types of rounding. So let's say, I'm just making something that was 5965. They would accept 2 different answers on that. They would accept 596 and 597, because you can round by truncating and just chopping off, or round up if it's 5 or greater on the next digit. They will accept either one.
Even if it's not 5.
I know, even if it's 5, actually if it's 6, they will. You can just truncate it. You can just chop it off. Absolutely. Okay, so here's the thing. It says you make this, and it says, are the approximate values overestimates or underestimates? What do you think? How do you know if this is going to be an overestimate or underestimate? What do you think? You want to see more with respect to tangent lines. Do you remember? Concave down means all the tangent lines are always above the function. Concave up means the tangent lines are always below the function. So if this is concave down, if the function, let's say, starts here and was concave down, all of the tangent lines, anywhere you take the tangent line, what are they going to be? Above, right? So if you started off above, what's going to keep on happening? You're going to stay above. So if this is concave down, then it is an overestimate. The question I have is, how do we know for certain if it's concave down? Take a look. It says, the results from Euler's method in table 11.3, along with the exact y values, calculated from the equation, which is the solution. Great. Since the curve is concave down, do you notice how it's just stated? How do we know for a fact that it's concave down? Do we know for a fact? The derivative is less than 0? Just because the derivative is less than 0 doesn't mean it's concave down. Do you understand what I'm saying here, everybody? The point is that we're pretty sure it's concave down, and that's enough right now. But the idea is, to show that it's concave down, we need to know that the second derivative is negative everywhere on that section, right? We haven't done that, right? Yeah. It looks like it is because it's getting bigger and bigger. You just have to be careful about it. Because for example, can you decrease and be concave up? Yeah, you can go like this, right? So you just have to be careful about it. Yeah. Or T, sorry, long and then T, yeah. The first derivative is decreasing. What do you mean by the rate of change of the first derivative? dy dx is, but just because dy dx is decreasing, look, you can go like this, that's concave down, right? And dy dx is what? Is always negative, right? But you can also do this. Isn't dy dx less than 0 there?
Yeah, but that one dy dx is increasing.
But the what is increasing?
Dy dx.
That's just the second derivative. You're saying
Decreasing and increasing rate.
So here's the thing. We've done 4 points, and it looks like what's happening. Point 1, and the distance is increasing, right? It's going down faster. Yes. How many points have we done again? 4 points. How many points are between any 2 points on a function?
Infinite.
An infinite. My point is, we very, very, very strongly suspect that this is concave down. But are these enough points to conclusively prove it?
No.
I'm just trying to make a point. You strongly believe it, but we haven't proven it. The difference between 99% sure and 100% sure, that's like all of math, everybody. Okay? Huge things result in that difference. Huge things. Because numbers without context are meaningless. We like to think like 0.99 is like an awesome percent because it's really close to 100. Well, what happens if the code is breakable or not? You know, like it matters a great deal. So you want to get closer and closer, but it's all relative. Okay, moving on.